Hypercompositional Algebra. In this series, we'll explore one of the most fascinating generalization of classical algebra, from the basic concept of hypergroups to modern research topics such as polygroups, hyperrings, hyperfields, and recent developments in the quantitative invariance. But let's begin with a simple question. Imagine multiplying two numbers and getting three different correct answers. Impossible, right? But this is not the case in hypercompositional algebra. Today we'll discover how this remarkable idea was born almost a century ago. By the end of this video, you will be able to answer 4 questions. What exactly is a hypergroup? How does a hyperoperation differ from an ordinary operation? Who was Frédéric Marty? And finally, why are hypergroups still an active area of mathematical research today? Since our first mathematics classes, we've learned that every operation produces exactly one answer. For example, 2 plus 3 is equal to 5. 5 times 4 is equal to 20. So every pair of elements produces one unique result. This principle is so natural that we rarely question it. But now consider situations outside pure mathematics. A chemical reaction, for example, it may produce several products. A decision can have multiple possible consequences. Many real-world systems are non-deterministic. And here you can look at some chemical reactions, some about Mendelian inheritance, some about the ABO blood group inheritance, and the RH blood system inheritance. So instead of one outcome, there may be several possible outcomes. So a natural mathematical question arises. Can we build an algebra where one naturally returns a set of possible results rather than a single element? The answer is yes, and this idea led to the birth of hypercompositional algebra. In classical algebra, an operation combines two elements and produces exactly one element. And this one, it reminds us of the addition of integers or real numbers or even complex numbers, the multiplication of these numbers. These things, the outcome is only one element. Hypercompositional algebra replaces this idea with something. Now, instead of the operation A star B to produce one element, we will have a set of elements. And here we can think of this example. If we take, let's say, this set, A, B, A with A, the operation is A with B, the operation is AB, and here B with A is AB, and B with B is B. This one is not a group point. This is not a binary operation. This is actually a binary hyperoperation. Because if you look at the hyperoperation or the result when A and B interact, a set rather than one element. "1934 was an important year in every algebraist life. This was the born of a new field of algebra, a generalization of algebra called hypercompositional algebra, and in some literature it's called as hyperstructure theory. This idea was introduced by the French mathematician Frédéric Marty. His motivation did not come from trying to invent something unusual. Instead, it came from a classical problem in group theory. And shortly, we'll know how. If you're interested, you can check his article that was or this result that was from a conference in 1934. Every student of algebra, specifically abstract algebra 1, in which we learn group theory, learns that if N is a normal subgroup of a group G, then the quotient G mod N is again a group. But what happens if the subgroup is not normal? It's just a subgroup. Classical group theory tells us that the quotient is no longer a group. Most mathematicians stop there. Marty asked a different question. Rather than forcing the quotient to remain a group, what kind of algebraic structure does it naturally become? His remarkable discovery was that the quotient of a group by any subgroup naturally forms a hypergroup. This elegant observation removed one of the strongest restrictions in group theory and opened the door to an entirely new branch of algebra. What began as simple generalization has since grown into a rich and active research area. Here's something that you would like to know about Frédéric Marty. Frédéric Marty was also an officer, and unfortunately, he died during the World War II at the age of 29. One more thing, that his father is also a mathematician, although he did not live that much, but he left an impact. Introduced hypercompositional algebra since 100 years, more than a century or around a century. And now we have lots of scholars, lots of algebraists. They are working on this field and on other applications for it. Now let's look again at the example that we showed before. Let's take H as A, B, and this is a finite set. This is A and this is B. And let's take this that we will call it, as we said, hyperoperation instead of binary operation. So this is a binary hyperoperation. A with A interaction, it gives A. A with B, it gives AB, and B with A, it gives a set, and B with B, it gives B. This one, as we said, it's not a group point. Here we have a hyperoperation, and this one, basically, later on in the other episode, call it as the biset hypergroup. So this one basically is a hypergroup, and this is the hypergroup of Marty. For a hypergroup, we have two pairs. Now, before we move to a hypergroup, let's recall for a group. Finite or infinite as well. Similarly, for hypergroup, it can be finite or infinite as well. However, in a group, we have only single outcome. In hypergroups, we have multi-outcomes. And in some literature, you will find instead of the word hyper, you will find it as multi-group. Now, the commutativity in a group is not important. Also in hypergroup, it's not a must. What is the must is the associativity and the reproductivity. And let's check them here. Associativity, it tells us that X round Y round Z is the same as X round Y round Z. So here, if we look here, if we take A round A round A, it means here to check A round A, and we need to check A round A round A. Basically, the left is A and the right is A. This is not enough in order to prove associativity. We need to check all the possible values for X, Y, and Z, and X round Y round Z, where X and Z belong to the set AB. I will keep it for you as a simple exercise to prove that the associativity here holds. What else do we need? To be a group, the reproduction axiom should be there, which means that XH is the same as HX is the same as H. Here it's very simple. How? All what we need, each column contains H. We highlighted the column in pink, and each row contains H as well. So the reproduction axiom is. Now you might ask, what about the identity? What about the inverse? The hypergroups that was defined by Marty, it didn't state that an identity should be there or an inverse should be there. But later on in the upcoming episodes, we will learn special classes of hypergroups, such as the canonical hypergroups, the quasi-canonical hypergroups that they are called as polygroups, in which an identity is very important to be there. So these are the main two pillars of a hypergroup, the hypergroup of Marty, the associativity, and the reproductivity. When Marty defined a hypergroup, he stated that we are starting with a non-empty set, and we are going to the power set, excluding the empty set. And of course, the associativity should be there, and the reproduction axiom should be there. And if we have a pair of elements of this hyperoperation as circ, A round B, it should be a non-empty set of H. It means it's not empty. This was a condition before he went to associativity. But recently, some hypercompositional specialists said that we can reduce this axiom. It means that it's not a must that the A for B to be non-empty, because this one is immediate result of having it associative and reproductive. Let's go through it quickly or briefly. Suppose that we have x and y in H with xy equal phi. If we apply the productivity, H is equal to xH. We expand as well, so H is equal xyH. Remember, xH is H for every x, and y is in H, so YH is also equal to H. Now this one, we can use the associativity, which is x, y, h. But we are xy equal to phi, so we will get phi h. Phi h is phi, but we are starting with h as a non-empty set. So this is very important because it's for a hypergroup that is associative and satisfies the reproduction axiom. No need to the binary hyperoperation should be in power star of H. It's enough to be in power of H, the power set we mean. So the remarkable discovery that was that the quotient of a group by any subgroup naturally forms a hypergroup is a very elegant observation. And again, as we said before, it removed one of the strongest restrictions in group theory. And in this way, by relaxing this condition, by allowing the hyperoperation or action between two elements to be a set or a non-empty set, it opens door for lots of other applications. Nearly 100 years after Marty's discovery, hypercompositional algebra continues to evolve. Researchers today study many related structures, including hypergroups, polygroups, hyperrings, hyperfields, fuzzy hypercompositional algebra, nitrosophic hypercompositional algebra. And these theories have connections with coding theory, cryptography, automata, geometry, chemistry, biology, physics, and many other disciplines. So hypercompositional algebra has become a vibrant area of research that combines elegant theory with exciting applications. This was just the beginning of our journey into hypercompositional algebra. This is just a brief intro. We did not go into technical definitions or other important things as well, but I promise that in the next episode, we'll formally define hypergroups, give examples, and discuss other things related to hypercompositional algebra. If you're interested in modern algebra, current mathematical research, or simply enjoy discovering beautiful mathematical ideas, be sure to follow this series. And if you would like to stay connected with me, you can scan this QR, connect with me on LinkedIn, and ask your questions. And of course, you can leave in the comments your or what you like to learn about hypercompositional algebra, or if you would like to know more specific books that they are important or specific articles. From now till we meet again, have a great day. See you inshallah in the next episode.